One difference is now there's one cause but two results. But this is the same tester. So I don't have to have different probability for tester 1 and tester 2. But the cause, cancer, is affecting to both testers. We have three parameters. The prior probability to have cancer is 0.01. And because of that, we can also derive probability of not having cancer, that is 0.99. Then from the second one, that is conditional probability. Probability of positive given C is 0.9. That means probability of negative given C is 0.1. Probability of negative given not C is 0.8. That means probability of negative given not C, positive given not C is 0.2. If I just use a Bayes rule for this one, I can say probability of C given positive and positive will be probability of positive and positive given C times probability of prior C divided by probability of positive and positive. This is Bayes rule. Or if we apply, we just learned, in this case, 1 over probability of positive is normalizer. And normalizer is 1 over prime plus negative prime. More calculations are needed, so I can just jump to the prime using prime. Numerator is just prime, so prime C given positive divided by normalizer is just 1 over prime and another prime. Another prime is, instead of C, not C, only prior changed. So prime C given positive and positive plus prime not C given positive and positive. This means I just need to calculate what is prime C given positive. This is the probability of the flip positive given C times the probability of C. I know probability of C, but I do not know probability of positive given C. Actually, this one is, those two, tester 1 and tester 2 are independent, but conditionally independent. They have same given. So we call they are as conditionally independent. So as long as they have given, they are independent. So I can rewrite probability of positive and positive given C as probability of positive given C, that is tester 1, and times the probability of positive given C. The second one is the tester 2. Then probability of C is still down. So when they have same condition, the same given, they work like independent. So just multiply. So final number, 0.0081 over 0.0081 plus 0.0396 is about, actually you can also solve by using the probability table. So usually prior goes in the first column. Prior, the probability of the prior, probability of C, which is 0.01, and probability of not C is 0.99. Then you can also put the given other probabilities, the probability of positive given prior. So that is 0.9, negative given prior cancer, that is 0.1. Positive given not C, that is 0.2. The negative given not C is 0.8. So you may also write all the numbers in the table, then use just those numbers. You can also calculate prime beforehand. So first prime represents the prime C given. The given is not changed, it's not observable, so positive and negative. And prime of not C given positive, negative. So if I use the prime definition, that is flip and prior, then flip, multiply, prior. Then because the positive two testers are conditionally independent. So I can write this joint probability as probability of positive given not C times the probability of negative given not C. Then there is a probability of not C. Now I have all those numbers, probability of positive C. So you can find the number from the table now. So if you calculate these numbers, and it's gonna be about 0.0009. Then second prime not C given positive and negative will be 0. Around 1584. So when I want to find the probability of C given positive and negative, it's gonna be prime over prime plus prime negative C, negative prior. Then if you plug in numbers, you're going to get 0.0056. So conditionally independent means when you have two nodes, they are independent, but they have the same code. So we call this one as given A, B, and C are independent. So what we used was the probability of B and C given A can be calculated as the probability of B given A times the probability of C given A. And if I have a probability of B given A and C, because B and C are conditionally dependent, it can be probability of B given A only. So C can be gone. You can go forward and also backward, vice versa. So tester 1 and tester 2 are conditionally independent. But the next problem is asking, what is the tester 2 is positive given tester 1. So when I do not use the tilde not, that means it's a positive. I need a code, actually the parent node. So I can write this one, change it to probability of tester 2 given tester 1 and the cause. So in this problem, if you go all the way up, the cause is cancer, so C. But I have to care about C is positive or C is negative, both cases. So I'm gonna say for each C. But actually, I cannot just add something for free. I have to pay for the cost for this addition. So in this case, you're supposed to multiply probability of whatever you just added into the given conditionally. When T1 happened, tester 1 is positive happened, what is the probability of CI? That's the one you have to multiply. Then I have to work on for each C value. When cancer is positive or when cancer is negative. So I have to get all the cases. It's gonna be or case, cancer or not cancer. So I'm going to add them, all the cases. So there's a sigma. So first I gave you how to start. So probability of tester 2 is positive, given tester 1 is positive, you can rewrite as tester 2 is positive, given tester 1 is positive, and C times the probability of C given tester 1 is positive, plus probability of tester 2 given tester 1 and not C times the probability of not C given tester 1. So each one is C's values, Ci becomes C, positive C, or negative C. Then, because tester 1 and tester 2 are conditionally independent, so the second one in the conditionally independence rule, if they are conditionally independent, you can ignore So I can rewrite tester 2 given C times the C given tester 1, and tester 2 given not C times not C given tester 1. Then tester 2 is a positive, means I can just use the positive. So I rewrote this one for my convenience because they are same tester. I know probability of positive given C. It's a given. But I do not know probability of C given positive. So I can use a Bayes rule. So use prime over prime plus prime not prior. That means flip times prior over flip times prior plus with not C times not C by the rule. Then now each one you already know the numeric values. So if you calculate this, you're gonna get about 0.0434. Okay, so I'm going to plug in 0.0434 for the probability of C given positive. How about probability of not C given positive? Oh, some of those two is 1. So I can do just simply 1 minus 0.0434 because they have the same given. Now you have all the numbers. Probability of positive given C is 0.9 from the problem on the top. Positive given not C is 0.2. So if you calculate all those numbers, you're gonna get 0.2301 around.